We're going to take a look at whether or not a function is either linear or nonlinear, and it's just what you think it is. If a function is linear, it behaves exactly like a straight line forever and ever. A nonlinear function either has some sort of curvature to it, or the line breaks into different slopes. And as you move on through your math and science life, you're going to really care about whether or not certain situations are linear or nonlinear. If a relation is presented to you as a graph, it's really easy for your eyeballs to see if it's linear or not linear. But if your equation or your relation is given to you in terms of a table, now it's a little bit more difficult. So we're going to take a look at what you would do in that situation. Now, one way to do this is to very, very carefully plot these points on a coordinate grid and then see if you have a linear pattern. And that's not looking too linear to me. The problem with this method that I just showed you is you have to be very, very precise with your graph, and it does take a little bit of time, but your eyeballs do tell you whether or not the function is linear. For the second example I showed you, I did the same thing. I carefully made a coordinate grid and I plotted each point, and in this case, assuming I was pretty darn careful, I can see a distinct linear pattern. So I can say that this one is linear, but I definitely can't say the other one is linear. So since graphing it is not always the best option, we're going to also use slope to determine if a function is linear. And basically, if as I go through this table or this table, the slope remains constant, I have a linear function. If the slope changes between the points, then the function is not linear. We'll show you how this works here in a moment. But before we show you how that works, let's take a look at this statement again. Linear functions have a constant slope. That slope is constant. It's always negative something. Looks like to be about -2. And then this function, which our eyeballs told us was non-linear, the slope is changing between the points. So it got a little bit steeper, a little bit less steep. So these two rules talk about the slope and they confirm what your eyeballs see. But let's use these two rules with the data table and pretend that we weren't going to take the time to graph. What I need to do is I need to treat each one of these as an ordered pair and then find the slope between each ordered pair. For example, between these first 2 points, I did my y minus y over my x minus x, and I got a slope of 2/3. Now I'm going to try the slope between the next 2 points. When I did the slope between these next 2 points, I did my y minus y over x minus x, I got a 2/1, and what I see here is the slope has changed. If the slope has changed, that means we have a nonlinear function, because linear functions have a constant slope. I would always get 2/3, 2/3, 2/3, 2/3. If the slope changes between the points, and it just changed right there, we have a nonlinear function. I'm going to do the same thing over here. We know this one's linear, so when I do the slope between all those points, I should get a constant slope. And sure enough, after I compute the slope from point to point, point to point, point to point, I kept getting a -2 for a slope, which meant my slope was constant. It never changed, and thus I have a linear function. So if you need to find out if a function is linear and you have a data table, check out their slopes. If the slope is always the same, you have a linear function. If the slope changes between the points, then you have a nonlinear function.